Hello everyone, and welcome. I'm excited to have you here today. We're about to dive into an important topic, NFPA 20 fire pump system, step-by-step design and sizing. In this presentation, we'll walk through the key steps involved in designing and sizing fire pump systems according to NFPA 20 standards. We'll cover everything from basic concepts to practical considerations. So, let's get started. Let's start with step 1, determine flow. Or what we call Q. This is all about understanding the water demand based on NFPA 13 and 14 standards. When it comes to sprinklers, the flow rate typically ranges from 500 to 1,500 gallons per minute, and this depends on the hazard density. That is, how much water is needed to control or suppress the specific hazard. For standpipes, the required flow usually begins at 500 gallons per minute, but if you have multiple standpipes, you add about 250 gallons per minute for each additional one. Keep in mind, there's a maximum flow, which generally falls between 1,000 and 1,250 gallons per minute. The key takeaway here is that the flow rate, or Q, essentially represents the water supply capacity needed to effectively fight a fire. It's a crucial first step, because knowing this helps us ensure the system is designed to deliver enough water when it's needed most. This step links directly to the overall fire protection strategy, making sure we're properly prepared to handle different hazards. All right, let's move on to step 2, determining pressure, or P. To do this, we use a simple formula. P equals the outlet pressure plus friction loss plus elevation head. First, the outlet pressure depends on the source. For a standpipe, we're looking at about 100 psi, which is roughly 7 bar. For sprinklers, it varies depending on the specific hazard demand, but it's important to remember that this pressure needs to be sufficient to cover the system's needs. Next, we account for friction loss. This occurs as water moves through pipes, fittings, and valves, and we typically calculate it using the Hazen-Williams formula. This friction reduces the pressure available at the outlet, so it's crucial to include in our calculations. Finally, there's the elevation head. For every foot of height increase, we add approximately 0.433 psi to our pressure calculation. This means that taller buildings require more pressure to push water to higher floors. By thoroughly understanding and calculating each of these components, we ensure our fire protection system has the right pressure to operate effectively across all parts of the building. This step is fundamental to designing a reliable and efficient system. Now let's move on to step 3, which is calculating the pump power, measured in horsepower. The key formula here is HP equals Q times P, divided by 3960 times eta. Q represents the flow rate in gallons per minute, and P is the pressure in pounds per square inch. Eta, or efficiency, typically ranges from 0.7 to 0.85, depending on the pump's performance. This calculation is crucial because it helps us determine the size of the motor or diesel engine needed to power the pump effectively. By understanding these values, we ensure that the equipment is properly sized for the application, leading to better performance and energy efficiency. So keep in mind, the more accurate your flow rate and pressure measurements, the more precise your horsepower calculation will be, ultimately guiding you to select the right motor size for your system. All right, now we're at step 4, which is selecting the pump type according to NFPA 20 standards. When choosing a pump, the most common type you'll encounter is the horizontal split case, or HSC. These pumps are popular because they are reliable, easy to maintain, and generally have a long service life. They're a solid choice for many fire protection systems. Another option is the end suction pump, which is more compact and economical. These are typically used for smaller flows or where space is limited. They're a good choice when you need a simple, cost-effective solution. Then there are vertical turbine pumps, which are ideal for specific applications such as tanks, reservoirs, or wells. These are designed to handle higher heads and are often used when the pump needs to be submerged or installed in a deep well. The key thing to remember here is that the selection really depends on several factors: the flow rate you need, the head or pressure requirements, the pump curve, and also practical considerations like available space and ease of maintenance. So, always think about these aspects together to choose the most suitable pump type for your system. All right, moving on to step 5, key points. First, it's crucial to ensure that the pump, driver, and controller all comply with NFPA 20 standards. This compliance guarantees that the system meets safety and performance requirements, which is fundamental for reliable operation. Next, before giving final approval, you need to verify the system's performance using a certified pump curve. This step confirms that the pump will deliver the expected flow and pressure under actual conditions. By following these points, we make sure that the fire protection system is both safe and effective, aligning with the overall theme of reliability and code compliance. So remember, checking for NFPA 20 compliance and verifying performance with certified data are key to a successful installation.